Hey, today we're going to learn how to compute derivatives in Cartesian coordinates to curves expressed in polar coordinates, in particular so that we can find the equations of tangent lines to points on those curves. Show you what I mean. Suppose we look at the polar coordinate curve r equals the cosine of 2 theta, the four-petaled rose that we looked at in a previous video. And we want to find the equation of the line tangent to that curve at theta equals pi over 6. Which is to say what we're going to be looking at today is how to compute the equation of this line in red right here. And we'll work out a formula that works for any polar coordinate curve r equals some function of theta, and then we'll apply it to the example that we were just looking at. We've already seen that to translate polar coordinates into Cartesian coordinates, we can use these formulas: y equals r times the sine of theta, and x equals r times the cosine of theta. And if we think of theta as a parameter, then we get that dy dx is equal to dy d theta divided by dx d theta, just like we did when we were studying parametric equations. And these derivatives are not difficult to compute. We have expressions for x and y in terms of theta. For example, y equals r times the sine of theta. We have to remember that r itself is a function of theta. So that to compute dy d theta, for example, we need the product rule. The derivative of the first and the derivative of r is dr d theta, times the second, which is the sine of theta, plus the first, which is r, times the derivative of the second, and the derivative of the sine of theta is the cosine of theta. So that gives this expression for dy d theta. And we do the same thing to compute dx d theta, and we get this expression here, where the minus sign is simply because the derivative of the cosine of theta is the negative sine of theta. And putting this all together, this gives us an expression for the derivative in Cartesian coordinates, dy dx, of the polar coordinate curve r equals some function of theta. And it's this expression right here. Okay, let's use what we just learned to find the equation of the tangent line in the example that we were looking at, which was the function r equals the cosine of 2 theta, the four-petal rose, at the point where theta is equal to pi over 6. We need the derivative at theta equals pi over 6 in order to find the slope of the tangent line, and we have an expression for the derivative that we just worked so hard to find. It's this crazy expression right here. And one of the things that we need to know to compute this expression is dr d theta, which shows up in a couple of different places. And from the definition of the function that r is the cosine of 2 theta, we easily get, using the chain rule, that dr d theta is negative 2 times the sine of 2 theta. And so we can rewrite our expression for dy dx because we know that dr d theta is negative 2 sine of 2 theta. And we also know from this right here that r is the cosine of 2 theta, so we can replace these two instances of r with cosine of 2 theta. And that gives us this expression here for the derivative in Cartesian coordinates of the polar coordinate curve r equals the cosine of 2 theta at any point theta. But we're looking for it where theta is equal to pi over 6 in particular. And plugging theta equals pi over 6 into that expression, we get this expression right here, where the places where it said 2 theta, we have pi over 3, because 2 times pi over 6 is pi over 3, and wherever we had a theta, we just have a pi over 6. And these are all values we can compute. We know the sine and the cosine of pi over 6 and pi over 3, so all that's left is to plug in those values and do some arithmetic. And I'm not saying that the arithmetic is especially fun, but it is just arithmetic, and you do it slowly and carefully, and you eventually work out that the derivative at pi over 6 is the square root of 3 over 7. And let's make ourselves a little room. This tells us that the equation of the tangent line is y equals the square root of 3 over 7x plus b for some value of b, and all that's left is to find that value of b. And to do that, we need to know what are the values of x and y when theta is equal to pi over 6. We know that for any polar curve r is some function of theta, we can find x and y through these two equations, y equals r times the sine of theta and x equals r times the cosine of theta. And the polar curve that we're looking at is the curve r equals the cosine of 2 theta, so we can replace the r's in these expressions with cosine of 2 theta, and we get that y is cosine of 2 theta times the sine of theta, and x is cosine of 2 theta times the cosine of theta. We're interested in the x and y values when theta is pi over 6. So when theta is pi over 6, y is the cosine of pi over 3, which is twice pi over 6, times the sine of pi over 6. And you work that out, and that's equal to 1/4. And similarly, at theta equals pi over 6, you can compute that x is equal to the square root of 3 over 4. Plugging these values of x and y into our equation, y equals the square root of 3 over 7x plus b, we get this expression here, 1/4 equals the square root of 3 over 7 times the square root of 3 over 4 plus b, and all that's left is to solve for b. And after you do the arithmetic, you find that b is equal to 1/7, and we have found the equation of the tangent line to the polar coordinate curve r equals the cosine of 2 theta, at the point theta equals pi over 6, it's y equals the square root of 3 over 7x plus 1/7. And here it is, just for entertainment, the tangent to the 4 petal rows, r equals the cosine of 2 theta, at the point theta equals pi over 6. We saw this picture before, but now we also have the actual equation of the tangent line. Okay, that was how to find tangents to polar curves. Have some fun with the homework. Look forward to seeing you in class.